Okay, perfect. Hello, everyone. My name is Lucas Fryzek, and today I'm going to be talking about debugging the v3dv Vulkan driver on Raspberry Pi. Before I get into that, just a little background about me. So I'm actually an Ottawa local, born and raised. I got into computer graphics, which eventually led me down the path of doing driver development, graphics driver development in high school. I studied computer science and got my Bachelor of Computer Science at the University of Waterloo in, graduated class of 2018. And I've been doing graphics driver development since my first co-op job from university in 2015. So this is now 10 years of graphics driver development for me. So before I get started, does anyone in the room know anything about graphics drivers or GPUs and developing on them? Okay. I have some intro slides to cover the absolute basics then. I'm going to start first with what are graphics APIs. This is going to be a very important topic that I'm going to be covering, so if you don't know it, pay attention. They define a standard way to interface with a GPU, and they provide APIs that let you do things like manage resources on the GPU, schedule workloads to run on the GPU, and issue commands that will do various things. And they also define shading languages, which are programming languages that will be compiled down and then run on the GPUs themselves, on their shader cores. And you might have heard of some of these graphics APIs, for example, Vulkan, or OpenGL, or DirectX. The bug that I'm going to be talking about in today's presentation is in the Vulkan driver. So we're going to be focusing just on the Vulkan API. Now, if you're not familiar with what a GPU is, it's a custom piece of silicon that's designed to accelerate graphics and compute workloads. So this can be like a discrete graphics card, or it can be just part of an SoC. And they have hardware-specific instruction set architectures to actually program the GPU. They have hardware-specific command interfaces for actually telling the GPU, hey, I want you to do this. And they also have hardware-specific formats that they need resources to be loaded into so that they can actually read them. If you just take a JPEG image and throw it at a GPU, it's not going to render it. And the GPU drivers are the piece that sits in between all of this. They implement a specific graphics API. They'll do things like compile the shading language from the API into the actual GPU ISA. They will translate the API commands into actual commands that feed into the command engine of the GPU. And they'll also do things like translate resources from generic formats into the formats that the hardware actually expects to read them in. And you can see there's a lot of stuff here. GPU drivers can get pretty complicated. I don't know if you've heard the stats before, but something like AMD GPU is like more Linux kernel than the rest of the Linux kernel. And that's just the kernel part of it. That's not even the user space part of it, which isn't even in that statistic. So they're not simple. And GPUs themselves are not simple. They have things like shader cores, fixed function hardware, memory controllers, command interfaces, and then a whole lot of other stuff. And this is only a 35-minute presentation, so I can't talk about everything. So the bug I'm focusing on right now is only really interfacing with the fixed function hardware of the GPU and the memory controllers of the GPU. Now, what's v3dv? Well, this is the open source Vulkan driver for Broadcom GPUs. You probably are somewhat familiar with this hardware from the Raspberry Pi. All the devices from the Raspberry Pi 1 to the Raspberry Pi 5 have Broadcom SoCs on them with Broadcom GPUs on them. v3dv is the Vulkan driver that's compatible with the most recent Raspberry Pis, so the 4 and 5. The older generations of Raspberry Pis, their GPUs are not powerful enough or don't have the right feature set to implement Vulkan, so they only run OpenGL. And it's part of the Mesa project in the Linux graphics stack. And you probably don't know what Mesa is unless you do a lot of Linux stuff, or I don't know you're familiar with Linux at all. So I'll cover a little bit of the Linux graphics stack as part of this introduction. So this is a bit of an old image, but you can see there's a bunch of different parts that are part of the Linux graphics stack. You have, for example, the compositor and window manager. You have like the Linux kernel at the bottom here that's actually talking to hardware. At the top, you have applications that are wanting to draw things on the screen in some way. And then right here in this green area, you have the user space graphics drivers. And so this is where Mesa exists. It's part of user space. It doesn't exist in the kernel. And it talks to the kernel through an interface called DRM. And the DRM interface exists within the kernel. And now what's the difference between these two things? The user space graphics driver actually implements the API. It has things in it like the shader compiler that will take, for example, GLSL shading language or the SPIR-V intermediate language, and it will compile it into the actual GPU-specific assembly instructions. It will do things like create the GPU commands. And then on the other hand, the kernel space driver acts as a safe interface to the GPU. So it will deal with things like scheduling work to go on the GPU, so multiple applications can use the GPU at the same time. And it also deals with resource allocation and lifetimes with an asterisk on that. There's a lot more detail in how resource allocation works, and it depends on the driver and the hardware. So just take that with a grain of salt. But today, we are just focusing on user space. We're just focusing on Mesa. And Mesa itself is a bit of a weird project. It has, it's not like one library. It's not like you build Mesa and that's it. Like, it has a lot of different things that are a part of it. It has drivers for lots of different hardware, and it has the user space implementation for some standards. So like it will have like libgl in it, which provides all the OpenGL APIs that an application will link against, but then libgl inside of Mesa will call into its own interfaces. So it's a little bit complicated, but the Vulkan side of it is a little bit more simple, and I'll be just focusing on that today, and I'll just be focusing on Broadcom today too. So to get into the actual bug that we're going to be looking at, one annoying thing about the Raspberry Pi GPU is that it's not very powerful. Another annoying thing about the Raspberry Pi itself is that it's an ARM device, and it can be pretty hard to find software on Linux that runs on an ARM device that actually stresses a GPU out. So in the work that Igalia does to develop the v3dv graphics driver, we sometimes have to get creative to find more interesting use cases to actually stress out the GPU and find edge cases that things like the conformance test suite don't test. And so we'll do things like run translation layers to run Windows software, or we'll try to capture traces of games running under Windows and try to replay them on the GPU. Or we'll go and we'll get Android and we'll have Android run on the Raspberry Pi because there's tons of mobile games that use Vulkan that we can test. And this is the way that this bug was actually encountered. This is a benchmark suite for Android devices. I can't recall the name of the benchmark suite right now, but we went to go run it to see performance testing of the GPU and how it compared in different versions against something a little bit more demanding. And we noticed that one of the benchmark tests started rendering all these magenta colors all over the screen in a strange way. And we're like, okay, this is a driver bug we need to fix now. So, stage one, we identified an issue for a bug we want to fix. Okay? So, since you guys aren't familiar with any of the stack, I'm going to talk a little bit about, how you can actually build Mesa and test things on it, and then how we're going to actually look at the bug, figure out what could be going wrong, and get an idea of how to fix it. So Mesa is open source. I love open source software because you can go look at the source code, you can build it yourself. If it's a really well-supported community project, there's people you can talk to. Mesa is one of those projects where you can find people and actually get access to sometimes even the vendors themselves. So you can talk to people who are actually designing the hardware. And so if to build Mesa itself, there's nice documentation on the docs.mesa3d.org website where you can see what dependencies you need to go build it, instructions for what you need to do. So you can just go clone it, read the docs. It uses the Meson build system. You can use the Meson build system to configure it. In our case, we want to configure it to build the Broadcom driver. There are some more details about building on Android that link covers that I left out on this slide. So don't worry about those. I will not be testing you at the end of this to see if you can build the Android graphics driver. But yeah, so you can compile it, and then you can run this Meson dev command to actually run applications that you have built with your the version of the graphics driver that you want to test with, instead of using the system graphics driver. And a nice thing to do is you can run the Vulkan info command, and you can see that the driver version ends in .99, which means you're running a development Git version, not a tagged release version. So we have an idea now about how to build Mesa to start looking around the issue and investigating. So how do we actually investigate a graphics bug? We have this proprietary benchmark application. We don't have source code to it. We could, contact the app developer, maybe get some information about what they're doing. But we do actually have one other tool we can use, and that's tracing what the application is doing. So in the graphics space, there's a very cool tool called RenderDoc. It is a very powerful graphics debugger. It hooks into a running graphics application. It can be a Vulkan application, OpenGL, DirectX. It works on Windows, Android. I think it also works on Mac and Linux. Well, it does work on Linux. And you can capture a frame of the running application and then inspect all the graphics API calls that were made in that frame. And you can even modify the state of some API calls. So you can play around with what it's doing to see if that triggers the bug or doesn't trigger the bug. So that's exactly what I did in this case. I ran RenderDoc. You can see on the bottom right here, I captured a frame. You can see a bunch of VK command draw calls on the bottom there. But I also did a little bit more, and I also dumped some of the data that was coming out of the application to see what it was trying to send to the application. And right off the bat, you can see there's something wrong. The application is sending this nice looking stone texture, and for some reason the driver is getting this purple mess where things look like they're overlapping and they don't look right. So this covers my stage 2. I made a reproducible, inspectable test case for what I'm doing, and so now I can get a better idea of what's going on, try to build some intuition around the problem. So the question now I'm going to ask myself is, why is it only rendered incorrectly sometimes? You saw in the first image that most of it looked okay, but on some weird edges, it was purple, but probably 80% of it looked fine. So let's start looking for some weird things within RenderDoc to get a better idea about why it's failing in this specific case. So the first thing I'll notice is that the purple on the texture is being shown at this MIP level 2, it says here. You can see on the texture viewer as well, it says MIP 3. Don't worry about the 2-3 not matching. The texture tool I was using uses 1-based indexing. RenderDoc uses 0-based indexing. They are the same MIP level. And if you're not familiar with what MIPs are, I will talk about that. These are a level of detail optimization that real-time graphics uses quite often. It's existed for a long time. The earliest GPUs supported MIP mapping, and the reason for it being is that it lowers the amount of texture data you need to load when you go to draw something. The idea being, when something is close to the camera, it takes up a lot of pixels on the screen. You probably want to load the full detail, resolution version of that texture. But when something's far away and it takes up, only a handful of pixels on the screen, you don't want to load the whole texture to render it. So instead, what you'll do is you'll store progressively lower resolution versions of the texture into memory, and then the hardware will decide at sampling time which resolution version of the texture it will load. And if it doesn't take up a lot of pixels on the screen, it will load a lower resolution one using less memory bandwidth and also using less of the GPU's texture cache, which improves performance. But MIP mapping, very common technique. There's applications in Linux we've run that would definitely test out MIP mapping, so I don't suspect MIP mapping is the only problem in this application. So what else is different? In the RenderDoc capture, we can see that it's using an ASTC UNorm texture format. If you don't do mobile development, you probably don't know what ASTC is. The acronym itself stands for Adaptive Scalable Texture Compression. It's a block compression texture format. You probably have heard of block compression texture formats like JPEG is. Everyone sees JPEG artifacts. There's the blocks on them. And this is a similar idea where it's going to break the image up into blocks and then compress those blocks, but it differs a lot from JPEG because it's designed to be decoded at a block basis, where JPEG you need to decode the entire image just to render a single block. So this is really nice for GPUs because at draw time they don't know what parts of the texture they're going to have to read, and the whole point of having a compressed texture is that so that you don't have to store a high resolution image in memory. So if we can just read one block and then decode the whole block as is, then we can save a lot of memory bandwidth. ASTC texture format, there's a lot of different compressed texture formats that have different size and algorithms that they use to encode. I won't go into the specific algorithm for ASTC, but I will note that it has a fixed 128 bits per block. So each block in the image is represented by 128 bits of information. And it has variable dimensions that affect the quality. So an example to show this, you can see there's an image of a bird from Wikipedia. The original image is at its original quality. Then there's a version of it at 4x4 block compression, 6x6 block compression, 8x8, and then 12x12. And you can see as the block size goes up, the quality goes down because you're trying to fit more information into those fixed 128 bits. So applications will typically try to find a sweet spot between the size of the block and the actual quality they want for rendering. Some other things to know about ASTC and that what the application is doing is that it's using a 6x6 block format, specifically the uniform normalized linear format, which is not important to this issue, but if you're looking at the screenshot, you would have seen that. The only thing to note about that is that if you want like HDR or sRGB, this is not the format you would use for it. I'm not going to go into color theory. That's like a whole presentation in of itself. I'm not a color theory expert either. So don't worry about that. Just worry about the fact that it's a 6x6 block format. And so yeah, each of the 128 bits represents 6x6 pixels. Another thing to know about ASTC, which is very interesting for this issue, is that if it can't decode a block properly, it will display the color magenta. I like the spec, what the spec authors wrote. This color has been chosen because it's much more noticeable than black or white and occurs far less often in valid images. It's very obvious that there was a problem going on in the scene. The magenta really stood out, so I think they made a good call deciding that. But ASTC on its own isn't the only weird thing. Like the conformance test suite tests ASTC, so come on, like what's going on? Like I would hope things tested it more. So let's keep looking. What else is weird about this? Well, we can see that in the image that the application is sending, we have this one shape in the stone, which we can see in the what the driver is actually rendering. And then we can see it again in another part of the image, but it's larger. And there's this shape right here, which we can see at one part of the image, and then we can see it again over here, but larger. And this gives us a little bit of an idea that perhaps the different MIP levels in the texture.
Just a quick question.
Yeah.
Can I ask questions?
Sure, yeah.
I'm just wondering what you're expecting to see on the bottom.
It should be exactly the same. It should be exactly the same as that. Okay. Yeah. So it's not the same, so there's a problem.
Okay.
So in the driver version of it, it looks like we might have two overlapping MIP levels. So when you see something where the texture and GPU memory seems to be overlapping, this usually is a problem with one or multiple of three things, which is the alignment, padding, or tiling of the texture. And if you're not familiar with alignment, padding, and tiling, I'll talk a little bit about them. Just important things to note. The GPUs will not tightly pack texture data. They are going to pick ways to represent the texture data that makes it really efficient for them to draw at runtime. And this can affect the alignment and padding of it, but also how the texture is represented. So I'll go into what I mean about that. But first, in case you don't know what alignment is, alignment is something that's used for hardware that can only load at specific aligned offsets. So this is not a GPU-specific thing. For example, if you're doing like vector instructions on the CPU, typically the vector data that you're trying to load into a vector register needs to be aligned to the size of the vector. So if you have like a 128-bit vector, all the data needs to be 128 bits aligned. And so what does align mean? Well, if we need 4-byte alignment, we have memory. It starts at address 0, goes on to whatever. I only went to 7 here because I have a finite amount of space on the slide. Then if we pick an address to allocate, it needs to be divisible by 4. So that can be 0, 4, 8, 12, 16 onwards. As long as it's divisible by 4, that's a safe address to use. Padding is a little bit different. It defines a minimum buffer size that needs to be allocated. And this is usually done because the hardware is going to load fixed amounts of memory, like a non-configurable amount. And so we will pad the buffer that we're allocating to the padding size so that we're not just loading random data, we're loading defined data that we've zero initialized or initialized to something safe that won't cause an issue. Next, there's the tiling. This is one that's probably less familiar and can be pretty strange to wrap your head around. If you know anything about drawing pictures on a computer, you probably are familiar with linear images. The idea being that each byte in memory represents a sequential pixel, and you go row by row. So byte 0, if you have a 128 by 128 pixel image, byte 0 will represent the first pixel in the image, then byte 127 will represent the 128th pixel on the first row, and then byte 128 will be the next row. And you just do that and you repeat until you have the entire 128 by 128 resolution image. This is nice to reason about. It's pretty simple, but it's really bad when it comes to drawing because it's not great for cache locality. Often when you draw something, you'll be sampling texture data from a random rectangle or a triangle inside the texture. And so it's really inefficient to have to load an entire row of pixels just to get to the next pixel on the next row. And so GPUs don't really like this. A lot of them can't actually load linear image data directly, or if they do, it goes into a lower performance mode, or the performance will be much lower to make it work. So instead, GPUs do something called tiling, where they'll group pixels into a tile. There's a lot of different ways they can do this, and it's hardware specific. One simpler way to do it is where each tile ends up being a smaller linear image. So for example, we could have a larger, 124 by 124 pixel image where each tile is 128 by 128. Inside the 128 by 128 tiles of the image, they're linear, but then instead of going all the way to the next row of the 124 by 124 texture, we just go to the next tile one over. And this is better for cache locality because we can load a tile in, which is usually it fits into the GPU texture cache, the cache lines of the GPU texture cache. And nearly every GPU supports some form of tiling. I think you'd have to go to really old hardware to find ones that don't, or really specialized hardware to find ones that don't. So this is stage 3. We've gathered context about the issue. We have some ideas of what's going on. It's using MIP mapping with ASTC texture compression, and the MIP levels seem to be overlapping after we get to the 3rd level. So now we can start looking at the hardware itself. What does v3dv expect for alignment, padding, and tiling? If we wanted to find this out, we could use the GPU spec. Unfortunately, Broadcom doesn't publish GPU specs. You need an NDA to look at it. Fortunately, Igalia does have NDA signed with Broadcom, so we can get access to the documentation. But for this issue itself, the code is really well documented, and so you can get a really good idea of what the hardware is expecting just from reading the comments in the code. And I've grabbed one comment that's really critical for this bug from the code. There's this function called v3d setup plane slices in Mesa that is responsible for allocating what's called an image plane, which is one slice of an image. If your image is 2-dimensional, that's the only part of it. If it's multi-dimensional, then it will be one slice in a multi-dimensional image. For our case, we just have 2D images. Don't worry about 3D images and how they actually get drawn or anything like that. We're keeping it simple. That's why I picked this bug. And so The comment itself tells us something about mipmap padding. It says, note that power of 2 padding is based on level 1 dimension. These are not equivalent to just util power of 2 dimensions because at level 0 dimension of 9, the level 1 power of 2 padded dimension is 4, not 8. There's some more information around this that I couldn't fit on the slide, but what this comment in the area of code is telling us about is that the level 0 and level 1 mipmap levels don't need to be padded. Level 1 or level 2 onward do need to be padded, and not only they need to be padded to a power of 2, it has to be a power of 2 based on the level 1 dimension size, not the level 0 dimension size. So this is a weird quirk of the hardware we have to keep in mind. Let's just look at what this code is doing to actually get that power of 2 dimension. So here's the code. Here's some of the code that's responsible for figuring out the padding. You can see at the top, it's going to calculate the power of 2 dimension, like the comment just said. I'll explain what this line of code is doing quickly. You can see just from the innermost part of the brackets, it calls this uminify. This is a utility in Mesa to perform the mipmap division. So you saw from the picture before, with the mipmap, you had the full resolution and then divided by 2 for the next dimension, and divided by 2 for the next one. So this is the standard way to do mip mapping, and this utility handles that. You give it the level 0 dimension and then a number to represent what level you want, and it will tell you what that dimension is supposed to be at that mip level, handling all the rounding rules for you for the division. So it's going to do that. It's going to take the original width of the image or the height of the image, and it's going to get the level 1 dimension. Then it's going to call this other utility called next power of 2. I hope that's pretty obvious what that does, but in case it isn't, it finds the power of 2 that's higher than it. So for example, if you have 48, the next power of 2 would be 64. That's the next power of 2 that's bigger than it. And then lastly, it's going to multiply by 2, which is effectively going to take it from the level 1 MIP level brought to a power of 2 to the level 0 brought to a power of 2. And the reason it does that is because then all of the uminify function calls that happen later, they expect the level 0 dimension, even though we don't need that dimension to be padded. For the cases where we do want it padded, we want to have the level 0 dimension so the utility function will work properly. Next, it's going to loop through all the different MIP levels of the image. So an image can have a bunch of different levels. And then if the level that we're looking at is not 0 or 1, we will take the level width, or we'll compute the MIP dimension size based on the original width and height. But for any other one, we're going to use this power of 2 to actually get the padding. And then there's this interesting part at the bottom here where it's going to convert from pixel dimensions to block dimensions. Most of the time, this is going to do nothing. If you have like a normal texture, the block dimensions are just like 1 pixel represents 1 block. But in our case with ASTC texture compression, we do have blocks. We have 6 by 6 pixel blocks. So this is going to take the dimension and convert it from the number of blocks in width and height to the number of pixels in width and height to the number of blocks in width and height. So what does this look like if we actually calculate it out? Well, we start with a 1024 by 1024 image. If we try to convert that to the number of blocks that actually represents, that's going to be 171 by 171 6 by 6 pixel blocks. And you can see just from the block version, there actually is some padding because 1024 is not divisible by 6, so we need a little bit more space to actually represent that. The first MIP level after that will be 512 by 512, or 86 by 86 blocks. Then the problematic MIP level will be 256 by 256, or 43 by 43 blocks. And then the third one will be 128 by 128, or 22 by 22 blocks. And you can see here for the actual division, there's nothing weird going on. The image we started with was a power of 2, so no weird rules for the hardware come into play here. We can just divide by 2 because everything's already a power of 2. Now, I noted before that the converting to block dimensions was a little bit interesting. So if we scan through the code some more, we can figure out, like, why is it converting to block dimensions? Why is that important? Well, you'll see if you scroll through that the alignment is actually based on the block size, not on the pixel size. Like you can see here, it's going to take the the width of that MIP level and try to align it to this thing called the UIF block width, which is the tiling format for the Broadcom GPU, its block width, which depends on the format itself and the GPU generation. So that's why it's in a variable here. But so that's interesting. The alignment is based on the block size, but the padding we did on the raw pixel size. So maybe the issue here is that the MIP padding also needs to be based on block size, not just pixel size. So this is a theory we can run with to see if this is in fact the bug. So if we go back to our table and we figure, okay, if we need to pad power of 2 on the block dimensions, how does that change stuff? Well, level 0 and level 1, they don't need to change. They don't need padding according to the comment, but level 2 does. So if we do that, instead of getting a 43 by 43 block dimension, we'll now have 64 by 64 block dimensions, which substantially increases the number of real pixels being padded from 256 to 384 in each dimension. And then we could do the same thing on the third. We go from 22 by 22 to 32 by 32, which again increases pretty substantially the amount of padding. So if this is the issue, it could explain why we're seeing so much purple in the texture and why we had things overlapping. There's a lot of padding that seems to be missing out here. We found some relevant code, gave us an idea about the problem, and we saw something weird about it that could explain the bug. Let's try to update the code to do this now. And it's not that complicated to update it. We can write a helper to actually calculate the MIP dimensions based on the block size. And this is similar to the code we saw before, where it's going to minify the original dimension, but then before it gets the next power of 2, we're actually going to convert it to block size. We'll have this div roundup function, which is going to divide by the block size, and whatever value we get, we'll round up, and then we get the next power of 2 dimension based on that. And I'm going to do something interesting at the bottom here. I'm going to take the padded dimension and convert it back into raw pixels. Don't worry about that right now. I'll make a note right before the end about why I needed to do that. But then we can just take that helper we just wrote and use it instead of the calculation that was done there. And that's really all we have to do. But it's also a good idea to update the comment. It's that the padding should be based on the block size according to our testing. And to actually test it, we found something relevant to change. Let's go test it. That was the bug. That's all it was. The padding is based on blocks, not pixels, and the code just didn't do that. It was not that complicated to fix it. And now that we've actually resolved it, we can submit our change upstream. Mesa, is an open source project. It's has a great community. If you want to do work on Mesa, you can just make an account on the Free Desktop GitLab. Free Desktop is the organization that hosts a lot of the Linux graphics infrastructure. You can create a fork, make an MR on that fork, and real people in the community will respond to you, give you feedback on your changes. And that's exactly what I did here. I actually had to make 2 merge requests for this change. So there is some code in that function that needs the original pixel dimensions for some calculations. And so that's why it was important. I didn't get it right the first time. I found that out afterwards. So I needed two MRs to actually fix what looked like a simple bug. So we submitted upstream, and we're basically done. That covers it. We identified the issue. We found a way to reproduce it and inspect it. We gathered context about what could be going wrong, found relevant code that we can use as a reference. We found something to change in that code, and then we confirmed it, fixed it, and we submitted our change upstream. That covers my presentation. I hope you learned some stuff about GPU driver development. If you have any questions, I'll take questions now. If you want to reach out to me, I have my personal email there and also my Igalia email right there as well. Yeah.
You kind of hinted at this with having multiple merge requests. From somebody who's completely outside of this, how long does this kind of detective work take? Did this take several weeks? Did this take several months? And this is not a reflection on you.
Yeah.
This is so beyond what I can comprehend.
It's
that process like?
So it really depends on the issue. Some of them like I can look at it and pretty quickly find out like, oh, this is what's going wrong, and like in a couple hours have a merge request up that fixes it. This specific one took me a little while longer because it's just when we started switching to testing on Android for Raspberry Pi, and we didn't have a setup originally where we could replace the driver that was being built in the Android image. So I think I ended up spending like 3 days on this bug, and like the first 2 days were just trying to get Android to let me replace the driver in it. That's why I didn't want to cover it in here. It ended up being a little annoying. I actually updated the documentation in Mesa to for Android for this and a couple other projects I've been working on. I've become a resident Android graphics guy at Igalia, not by choice, by necessity. Yeah, I think it probably took me about a day to debug it when I actually was able to inspect it and look at it. But there's some times where I have a bug where I'll look at it for like maybe a week, maybe even 2 weeks if it's like really complicated. And especially in those cases, I will try not to just look at that bug, like take a break and look at other stuff, because there's always other issues to work on or new features to implement, because Vulkan is still being updated, you know. There's new features, and so we got to stay on top and implement them if we want to stay conformant.
Nice, thank you.
I think you had your hand. Oh, sure. Okay.
I'm wondering why you ended up chasing this bug in the beginning. Like, you said that you had a demo and you captured the calls and you saw the problem, but wouldn't you have had something before that made you look for the problem?
Yeah. So we were testing originally on Android for 2 reasons. One was to get better performance data about how that driver performs in like real applications, because there isn't as many on like Linux that really stress the GPU, especially for a low-powered ARM device. And the other thing was to find bugs that we're totally missing right now. Because one thing that's very common for graphics driver development is you're never totally comfortable that any application will run fine against your driver. Like there's a whole ecosystem of Vulkan applications out there, and you can't test all of them. And so you want to try to increase the amount of applications you test. And so that's what we're doing here with Android as well. Like we're trying to find apps that we're not currently testing to see if there's bugs in our driver that we should be going to fix. Yeah?
For render docs, can you use that with like WebGL and like WebGL things?
I don't know if it works with WebGL.
Like this angle, like the Chrome or whatever, just translates the call as angle.
Yeah, so, okay, I know that, so if you're not familiar with the Igalia, we do a lot of different works on like different open source components. I know the people who work on some of the web GPU stuff use RenderDoc to debug the Vulkan calls that are generated by the browser runtime. But I don't know if you're like an application developer building, like a web GL or web GPU web app, if RenderDoc works to help you debug. Because I don't know if I mentioned this, but RenderDoc is not meant for driver developers. It's actually an application that was originally built for graphics application developers, specifically like game developers. It happens to be really useful for driver development, which is great, but it didn't start that way. And so I don't know if it works for if you're doing web GPU or web GL. Yeah, so you could probably look that up. It's probably right on their homepage or something. Any other questions? Yeah?
Do you have to look at performance problems as well, or is the GPU is so much faster it doesn't really matter how much time is spent on the driver?
So we do look at performance, yeah, and I've looked at performance bugs. Those are usually the ones that take a lot longer to figure out what's going on, because there's a lot of moving parts that can affect performance. And if you're interested in the performance side of it, there's some tooling in like Mesa that people use to help figure out what's going on. Like for example, a lot of the drivers in Mesa can emit Perfetto data with with GPU timestamps, so you can see like how long something actually takes to execute on the like a specific engine of the GPU, and we'll use that a lot of the time to narrow down what's going on. You know, if this is like a memory bandwidth problem, like we're not packing data in an efficient way, or maybe it's like not cache friendly, or things like that. And then the other thing too is like there is a shader compiler in there, and it could be that the shader compiler is not emitting instructions in a way that's optimal to render this, and maybe if we do a different kind of optimization in the compiler, then it can you know, render that particular workload better. Okay. Thank you very much.